Good morning, everyone. I am Aryan Rajguru.
And I'm Aryan Goyal, and today we'll be presenting our case study and simulation on Intel Core Skylake architecture, one of Intel's most significant processor designs.
Our presentation is divided into two main parts. First, a detailed discussion on Skylake architecture, design, and unique features. And second, a live simulation where we will demonstrate assembly programs running on an emulator.
So without further delay, let's begin with an overview of the Intel Skylake architecture.
To start with, Skylake represents Intel's sixth generation core architecture, launched in 2015. It's based on a 14 nanometer FinFET process, providing a balance between performance and power efficiency. It follows the x86-64 CISC architecture, which means it supports complex instructions but internally converts them into simpler micro operations for faster processing. Key goal behind Skylake design were to increase IPC instructions per cycle and reduce latency and improve energy efficiency across a wide range of devices, from laptops to servers. Now that we have general understanding of the architecture, let's move on to its design type and target applications.
Okay, so moving forward, Skylake belongs to the CISC family but incorporates RISC-like execution internally. This hybrid design allows it to handle both complex and simple instructions efficiently. It was developed with versatility in mind, supporting multitasking, gaming, AI acceleration, and video rendering. Skylake powers Intel Core i3, i5, i7, and Xeon E3 processors, aiming to deliver consistent performance across all workloads. With that covered, let's proceed to understand the instruction set architecture that defines how Skylake operates at the machine level.
The instruction set architecture or ISA of Skylake is based on x86-64 and includes advanced extensions such as AVX2, FMA3, and BMI 1 by 2. It supports multiple addressing modes, which provide flexibility in how data is accessed and manipulated. For example, the instruction MOVEAX demonstrates dynamic memory addressing capabilities, allowing efficient data access during execution. Having understood the ISA, let's now take a look at how the data flows within the processor, that is, the data path and pipelining structure.
Okay, so the Skylake pipeline consists of around 14 to 19 stages, which are divided into three major sections: the front end, the scheduler, and the back end. It utilizes out of order execution and features 8 execution ports, which allows multiple instructions to be processed simultaneously. Another key feature is the micro-op cache, which stores decoded instructions, enabling faster reuse and improving both performance and power efficiency. Now that we have explored how data flows through Skylake, let's move on to understand its memory hierarchy.
Each core in Skylake has a well-organized memory hierarchy, including 32 KB of L1 instruction and data cache, 256 KB of L2 cache, and 2 to 8 MB of shared L3 cache. It also supports DDR4 memory with a bandwidth of up to 34 GB per second, ensuring faster data access and reduces bottlenecks. Next, let's talk about the specialized features that make Skylake stand out in terms of parallelism and advanced processing.
So Skylake comes equipped with several specialized features such as hyperthreading, SIMD, vector processing, and Intel SGX AES-NI for enhanced security. It also supports virtualization technologies like VTX and EPT, as well as TSX for transactional synchronization. These features together contribute to greater speed, multitasking capabilities, and security. Having looked at these, let's move forward to discuss Skylake's multi-core structure and virtualization support in more detail.
Desktop variants of Skylake CPU actually features 2 to 4 cores, while Xeon versions can scale up to 28 cores. The architecture employs ring or mesh interconnections, allowing the efficient communication between cores and cache. An integrated memory controller further reduces latency, improving overall performance across parallel workloads. With that understanding, let's now look back at Style's historical context and how it compares with other architectures.
Skylake was basically the top phase in the Intel's famous tick-tock model of processor development, representing a major architectural improvement. It paved the way for its successors, Kaby Lake and Coffee Lake, which built upon Skylake's foundation. When compared to ARM structured architectures, Skylake focuses more on raw performance and high processing power, while ARM prioritizes power efficiency. Now that we have covered the theoretical aspects, let's move on the simulation section of our presentation.
So, now that we have explored the architectural details, it's time to see Skylake in action through our simulation.
We will be demonstrating two programs, Factorial and Fibonacci, both written for the Cross-86 architecture to showcase instruction, flow, and control.
The first program that we will discuss is the factorial program. The registers are initialized with RAX equal to 1 and RBX equal to 8. The program multiplies values in a loop using the IMUL instruction, decrements RBX after each iteration, and checks the loop condition using CMP and JG. Finally, the result, that is 4032, which we will see when the code is run, is stored in RAX, demonstrating both arithmetic and control flow operations in assembly. Now, let me share with you the screen demonstrating our code running on the stimulator. Give me just a second. So right now we are on a Word file where I saved our code for factorial program. Let's just copy it. And let's move to our stimulator. As you can see right now, we have opened the stimulator. Here we will be pasting our code. We will then save the code. And now it's time to run it. So as we can see, after running the code, it successfully gives us the required output, that is factorial of 8, which is equal to 40320, which was our main aim behind performing this program. Now moving on, let's discuss our second demonstration, the Fibonacci program.
Okay,
For that, I will just start sharing our PPT again. Yeah, over to you, Aryan.
okay, so let me take over for the Fibonacci program. Uh, Let me share my screen first. The Fibonacci program generates the first 10 Fibonacci numbers using the ADD instruction and simple loop control. The output sequence is expected to be printing Fibonacci numbers between 0 and 34, including 0 and 34. This program demonstrates efficient movement of data and iterative control flow within the x86 environment. So let me just share my screen, showing you the code. Just give me a second. Okay, so this on the screen you can see is the code for printing the Fibonacci numbers. Let me just copy it Okay, and paste it on the emulator. So we are right now at the emulator. Let me just paste my code here and save the file. I will compile the code first and then run it. So now you can see that the code is running successfully and it has printed the expected output, which was Fibonacci numbers between 0 and 32. So with the demonstrations complete, let's conclude our presentation here.
All right. The Intel Core Skylake architecture marked a major leap in Intel's processor evolution, offering higher IPC, better efficiency, and greater scalability.
It also laid the groundwork for future designs such as Kaby Lake and Coffee Lake, setting new standards for performance and reliability. With this, we would like to conclude our presentation.
Thank you very much, sir. Thank you.